Good morning! We are your presenters for today. I am Gabriel GUZMAN, and along with me is Melody CAGAANAN and James REYNOSO. Today, we are assigned to discuss one of the topics that we have gone through in our differential equation subject, which is electrical circuit. As we all know, differential equations have a fundamental importance in engineering mathematics because all physical laws and relations appear mathematically in the form of such equations. In this case, we're going to tackle about how it applies in electrical circuits. A simple closed electric circuit is one in which a resistance R and an inductance L or a capacitance C are connected in series with a source of electromotive force or EMF of E volts. The differential equation necessary to solve the various problems relative to this circuit is derived with the use of laws of Ohm's and Kirchhoff's. The following are important equations that signify the relationship of each variable in a given circuit. The resistance R in ohms is a circuit parameter which opposes the current I in amperes, causing a voltage drop of the voltage source in respect to resistance is equals to resistance times the current. The inductance L in Henry is a circuit parameter which opposes a change in the current I, causing a potential drop of the voltage source in respect to inductance is equals to inductance times the derivative of the current with respect to time. The capacitance C in farad is a circuit parameter which opposes a change in the voltage. The potential drop across the capacitor is the voltage source with respect to capacitance is equals to Q divided by the capacitance. Take note here that Q is the electric charge measured in coulombs. The current I is the rate of change of the electric charge Q, or I is equals to the derivative of Q with respect to time. These are the common units and symbol used in an electrical circuit. You can see that some of the terms that we have already discussed is seen there along with their letter representation and symbol representation. Now, speaking of electrical circuits and the units and symbol used in its diagram, let's go ahead and discuss the two kinds of electrical circuits that we are to review in this video. First is RL circuit. An RL circuit, or a resistor-inductor circuit, is an electrical circuit composed of resistors and inductors driven by a voltage or current source. A first-order RL circuit is composed of one resistor and one inductor and is the simplest type of RL circuit as shown in the diagram. The formula used to evaluate the RL circuit is given by the Kirchhoff's voltage law, which states that the algebraic sum of all the potentials around a closed electrical circuit is zero. Applying this law for an RL circuit, we have the voltage E is the inductance L, Henry in units, times the derivative of the current, amperes in units with respect to time, plus the product of the resistance R, ohms in units, and the current I. The next one is RC circuit. It is a circuit consisting of a simple loop containing a capacitor and a resistor in series with a voltage source as illustrated by the diagram being shown. It is also evaluated using the formula given by Kirchhoff's law, which is the total voltage E is the resistance R, ohms in units, times the derivative of the charge Q, coulomb in unit, with respect to time, plus the quotient of charge Q and the capacitance C, which is farad in units. Lastly, we must take note that the major difference between RC and RL circuit is that the RC circuit stores energy in the form of electric field, while the RL circuit stores energy in the form of magnetic field. The RC circuit is formed by connecting a resistance in series with a capacitor, and a battery source is provided to charge the capacitor. The RL circuit is formed by connecting a resistance with an inductor, and a battery source is also provided to supply the current to the inductor. To show you how these concepts are applied with first-order differential equations, let's go ahead to our exercises.
So for our exercises, I will be showing you two problems and how to solve these problems as well. So for our first example, this problem is an application of first-order differential equations in electrical circuits, specifically RL circuits. So our first problem is an inductance of 1 Henry and a resistance of 2 ohms are connected in series with a constant EMF of E volts. If the current is initially 0 and is equal to 10 amperes after 5 seconds, find E. So in this problem, we are tasked to find E, or the voltage source, and then we have two conditions. So the first condition is if the current is initially 0, and then the second condition is the current is equal to 10 amperes after 5 seconds. So we know that our formula for RL circuits is equal to L di over dt plus IR is equal to E. So what are we going to do here is we will just substitute the values given in our problems to our formula. So we have here 1 Henry. We know that Henry is in terms of L, so we will just substitute 1 to L. So we have 1 and then di over dt plus, we have resistance of 2 ohms, so we will substitute 2 to R, 2 times I. So we just copy I since we are not given of the current yet, or the value of the current yet, so it is equal to E. So E here is what we are finding, or the voltage source. So we will simplify dI over dt excuse me, plus 2I equals E. So if we are going to solve this one, we will transpose 2I to the right part. So we will have di over dt equals E minus 2I. So this equation, di over dt equals E minus 2I, is a differential equation that can be solved using separation of variables. So if we are going to use separation of variables, or the method separation of variables, we are going to isolate variable I together with its differential di from the differential dt. So what are we going to do is, first we will cross multiply dt to E minus 2I. So we will have di equals E minus 2I times dt. And then we will divide E minus 2I to both sides. So we will have over E minus 2I. And so we will get di over E minus 2I equals dt. So in this equation, di over E minus 2I equals dt, we already isolated the variable I together with its differential di from the differential dt. So what are we going to do is that we will integrate the equation. So we will have integral of di over E minus 2I equals the integral of dt. So before we can solve for the E, or before we can integrate this equation, we will first go back to our two conditions. So we know that our first condition is the current is initially 0. So when we say that the current is initially 0, we can assume that time is also 0. So we will write here at t equals 0. So current, or I, is equal to 0. So our second condition is that the current is equal to 10 amperes after 5 seconds. So at t equals 5, I equals 10 amperes. So in order to solve for the E, or the voltage source, we can use these conditions as our limits for integration. So before we use our conditions as limit for integrations, so we know that the left part, or the integral of di over E minus 2I, is in terms of variable I, and the right part, or the integral of dt, is in terms of t. So as we use the conditions as our limits, so we will have at t equals 0, So we will put t equals 0 in our integral of dt, since our integral of dt is in terms of time. So at t equals 0, current is 0. So we will put our current 0 in our as a lower limit for our integral di over e minus 2i, since this is in terms of variable I. So 0. And then at t equals 5, so at t equals 5, I equals 10 amperes. So I equals 10. So as you observe, our first conditions are our lower limits, and then our second condition is, are our upper limits. Okay, so we can now integrate this one, but first we will let u, because this is the most easy way, and through this we can solve for the voltage source. So we will first let u equals e minus 2i. So du equals negative 2 di. So our du is negative 2 di since we are integrating in terms of di or in terms of variable I. So any term that is not in terms of variable I will be considered as constant, and this includes the e. So it's negative 2 di, and then I will get the di, so I will divide du into negative 2. So I will have negative 1/2 du equals di. So since we have finished letting our u, we will now substitute our let u and du values to our integral of di over e minus 2i from 0 to 10. So we will now have integral of negative 1/2 du over u from 0 to 10 equals the integral of dt from 0 to 5. Then we transfer negative 1/2 in the left part of our integral sign. So we will now have negative 1/2 integral of du over u from 0 to 10 equals integral of dt from 0 to 5. So we know that du over u is equal to ln u, and so we will have negative 1/2 ln u evaluated from 0 to 10 equals the integral of t evaluated from 0 to 5. So now that we already have our ln u, all we need to do is we will substitute e minus 2i to our u, since we have let e minus 2i as our u earlier. So we will now have negative 1/2 ln e minus 2i evaluated from 0 to 10 equals the integral of t evaluated from 0 to 5. So we can now evaluate this one. So evaluating this, we will get negative 1/2 open close bracket ln e minus 2 times 10 minus ln e minus 2 times 0 equals 5 minus 0. So we simplify, we'll get negative 1/2. So open close bracket ln e minus 20 minus ln e equals 5. So we will, in the equation, negative 1/2 times open close bracket ln e minus 20 minus ln e equals 5. We will multiply negative 2 to be able to get rid of the negative 1/2. So if we multiply negative 2, we will be left with ln e minus 20 minus ln e equals negative 10. So following the properties of natural logarithm, we know that if there is a difference of 2 ln, the minuend will be the numerator and then the subtrahend will be the denominator. So if we apply the properties of natural logarithm, we will be having ln e minus 20 as the numerator, and then e as the denominator, equals negative 10. So after this one, we will make the equation ln e minus 20 over e equals negative 10 as an exponent of small letter e, or the Euler's number, so that we can cancel ln. So we will have e raised to the power of ln times e minus 20 over e equals e raised to the power of negative 10. So e raised to the power of ln will be cancelled, and so we will have, or we will be left with e minus 20 equals e raised to the power of negative 10. So what are we going to do next is that we will isolate big letter e, or the voltage source, so that we can get its value. So what are we going to do is we will cross multiply the voltage source to e raised to the power of negative 10. So we will have e minus 20 equals voltage source times e raised to the power of negative 10. And then we are going to transpose the right part, or the e times e raised to the power of negative 10 to the left side. And then we will transpose negative 20 to the right side as well. So we will have e minus e times e raised to the power of negative 10 equals 20. So isolating big letter e, or the voltage source, we will be having e times 1 minus e raised to the power of negative 10 equals 20. So we have e equals 20 over, or divided by 1 minus e raised to the power of negative 10. So from this equation, e equals 20 over 1 minus e raised to the power of negative 10, we will be getting the value of the voltage source. So using our calculator, we will solve for the voltage source. So we have 20 over 1 minus e raised to the power of negative 10. So we have e equals 20 times 0.00090804 volts, or we could have e equals 20.0009 volts. So from this value, we already have our voltage source, and so our final answer is the voltage source is equal to 20.0009 volts. So for our second example, this problem is an application of first-order differential equation in electrical circuits, specifically RC circuits. So the problem is a resistance of 10 ohms and C equals 0.1 farad is connected in series with a 12 volts battery. Find the charge at any time and the charge and the current 0.4 seconds after the switch is closed. So we know that the formula for RC circuits is R times dq over dt plus q over c equals E. So what are we going to do is that we will substitute the values in our problem to our formula. So we have here a resistance of 10 ohms. So we will substitute 10 to R since we know that resistance is in terms of R. So we have 10 dq over dt plus q. So we will just copy q since it is the one that we are finding. So it is not yet given. So over 0.1, since we are given with C equals 0.1, so we will just substitute 0.1 to C in the formula, equals, so we have here 12 volts battery, so we know that volts is in terms of E, so we will substitute 12 to E in the formula, so we have equals 12. So in order to get rid of 10, we will multiply the whole equation with 1 over 10. So multiplying it, we will be getting dq over dt plus q over 10 times 0.1 equals 12 over 10. So simplifying this one, we have 10 times 0.1. So we have dq over dt plus q. Since 10 times 0.1 is equal to 1, equals 12 divided by 10. We have 1.2. So this equation, dq over dt plus q equals 1.2 is an example of linear differential equation. So in linear differential equation, we will be getting p of x and then q of x. So our p of x here will be 1 since the coefficient of our q here is 1. And our q of x will be 1.2. So we know that the formula in linear differential equation is equal to q e raised to the power of the integral of p of x equals the integral of q of x times e raised to the power of the integral of p of x dt. So we will first get the integral of p of x so that we will just substitute the values later. So getting the integral of p of x, we will have the integral of 1 dt. So we know that the integral of 1 dt is equal to t. So we now have the value for the integral of p of x. We will just substitute the values to our linear differential equation formula. So we have q, e. So our integral of p of x is equal to t. So we will raise it to t equals the integral of q of x. So our q of x is 1.2. So we will put 1.2 here. And then e raised to the power of t, e. And then we will transpose 1.2 to the outside of the integral sign. So we have q e raised to the power of t equals 1.2 integral of e raised to the power of t dt. So evaluating e raised to the power of t, we are following the basic formula in integrating exponential functions. So in integrating exponential functions, if we have integral of eu du, we will be getting eu. So the same situation here in the integral of e raised to the power of t dt. So our e raised to the power of, our integral of e raised to the power of t dt is simply e raised to the power of t. So we will have q e raised to the power of t equals 1.2 e raised to the power of t plus c. So this q e raised to the power of t equals 1.2 e raised to the power of t plus c is our partial general solution, since we cannot yet get the charge using this one because the value of c is not yet given. So we are going to solve for the value of c. So how are we going to solve for the value of c? So we will assume that in t, at t equals 0, I equals 0, and definitely charge is equal to 0 also. So we will substitute the values that we assume to our partial general solution. So we will have 0 e raised to the power of 0 equals 1.2 e raised to the power of 0 plus c. So this is already 0 times 1, so this is 0 equals 1.2. So e raised to the power of 0, it's equal to 1. So we will not write it anymore. So 1.2 plus c. So we will have the value of c as negative 1.2. So we have c equals negative 1.2. So we will substitute the value of c in our partial general solution to be able to get our general solution. So we have q e raised to the power of t equals 1.2 e raised to the power of t minus 1.2. So q e raised to the power of t equals 1.2 e raised to the power of t minus 1.2 is our general solution. So from our general solution, we will be getting the charge at any time and the charge and the current 0.4 seconds after the switch is closed. So how are we going to do this? So from our general solution, we will divide e raised to the power of t to our general solution. So we will be left with 1.2 e raised to the power of t minus 1.2 over e raised to the power of t. We will be left with q equals 1.2 minus 1.2 over e raised to the power of t, or it could be q equals 1.2 minus 1.2 e raised to the power of negative t. So this is now our charge at any time. So I repeat, our charge at any time is q equals 1.2 minus 1.2 over e raised to the power of t, or it could be q equals 1.2 minus 1.2 e raised to the power of negative t. So after, we are going to find the charge 0.4 seconds after the switch is closed. So at t equals 0.4 seconds, so we will just substitute 0.4 seconds to the t in our charge at any time. So we will be substituting this one. So we will get q equals 1.2 minus 1.2 e raised to the power of negative 0.4. So solving this one, we will get 1.2 e raised to the power of negative 0.4. So we have 0.39561594448 coulombs. So our charge 0.4 seconds after the switch is closed is 0.396 coulombs. So the next thing we are going to find is the current 0.4 seconds after the switch is closed. So from our formula, R dq over dt plus q over c is equal to E, we can get current, or we can solve for the current. So we know that the current is, or I is equal to dq over dt. So this is the formula of current in RC circuits. And our Q is 1.2 minus 1.2 e raised to the power of negative t. So if we evaluate our Q, we will be getting 0 minus negative 1 times 1.2 e raised to the power of negative t. Okay, so we will simplify this one. So we will get 0 plus 1.2 e raised to the power of negative t. And so we will have 1.2 e raised to the power of negative t. So our I at any time will be 1.2 e raised to the power of negative t. So we are tasked to find the current 0.4 seconds after the switch is closed. So at t equals 0.4 seconds, what is the current? So we will use our formula, or we will substitute 0.4 seconds to 1.2 e raised to the power of negative t, since it is our current at any time. So we will have I equals 1.2 e raised to the power of negative 0.4. So using a calculator, We will solve for our current after 4 seconds, or 4 seconds after the switch is closed. So 1.2 e raised to the power of negative 2.4, or 0.4. We have I equals 0.80438405552 amperes. So we will just use up to 3 decimals, so we have 0.804 amperes. So this is it. We already get the current 0.4 seconds after the switch is closed, and it is 0.804 amperes. So repeating all the answers that we get, so our charge at any time is Q equals 1.2 minus 1.2 over E raised to the power of T, or it could be Q equals 1.2 minus 1.2 E raised to the power of negative T. And then our charge 0.4 seconds after the switch is closed is 0.396 coulombs. And then our current at any time is 1.2 E raised to the power of negative T. And then our current 0.4 seconds after the switch is closed is 0.804 amperes. And that is our final answers.
That's it for our instructional video about the applications of first-order differential equations, particularly in electrical circuits. I hope you learned something from us. Thank you for watching.